Hi, welcome back to Moose and Chemistry. This is Electron Configuration of Cerium CE lesson. Alright, Cerium is number 58 on the periodic table, and it's in the upper. Just kind of give you a hint of things to come. Alright, and so its atomic mass unit, AMU, is 140. Pretty darn cool, huh? These atoms are getting pretty big and heavy. So we got 58 protons, 58 electrons, and what about our neutron count? We're going to go AMU minus the number of protons equals the number of neutrons, right? So you can go 140 minus 58 is going to give me 82 neutrons. So we need 82 neutrons to do the job. There we go. All right, let's make that 2 a little bit better. What do you say? And let's write that 2 again. Much better. All right, now let's go ahead and let's get rid of this excess stuff here real quickly. And now we're getting into our electron configuration. So now we got to be really careful with our electron configuration because this is going to be an interesting one. S has 2 electrons, P has 6 electrons, D has 10 electrons, F has 14 electrons. And we're going to use the off-ball principle, which clearly states that we fill the lower shells first before we fill the upper shells. And we're going to do this by following the diagonal rule. So we just follow these red arrows down until we run out of electrons. So let's go and get started. 1s2. Yee doggy, yeah. 2s2. See, now we're moving. And then we go 2p6, 3s2. Pretty cool, huh? 2p6, 3s2. Then we go 3p6, 4s2. We go 3d10, 4p6, 5s2. 3d10, 4p6, 5s2. 4d10, 5p6, 6s2. Now, here's the cool thing. Now that cerium is in the F block, we have to recognize that it's in the F block, so we're going to go 4f1, 5d1. 4f1, 5d1, right? Yes. And that's going to be it. You count those up, we should be using 58 electrons. So let's double check that. 10, 20, 30, 40, 46, 48. This again, 2 and 2 and 6 make 10. That makes 20. That makes 30. That makes 40. 48. So it's 48, yep. 58, there we go. There's 58 electrons there. All right, snarls, huh? All right, so now, what are we going to do next? Well, we're going to do our orbital notation. And orbital notation deals with Hund's rule, remember? Hund's rule states that you have to fill an up arrow in each suborbit of that particular orbit, and then you can start the down arrows inside those orbits of those suborbits. So watch this. Up 1, down 1. Up 1, down 1. Here's a good example of Hund's rule. 2px, 2py, 2pz. Then we go down, down, down. Pretty amazing, huh? Up and down. Then we go 1, 2, 3, then go down. See that? Wow, that's cool. Up and then down. 1, 2, 3, 4, 5. Then we go down. Pretty darn snarly how this works out. Okay, then we go up, 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 and then we go down, down, down. And you go up and down again. And now we go, here we go, 4d10, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And then, of course, 5p6, right? 1, 2, 3, 4, 5, 6. 6s2, go up, go down, give 4fz3 cubed 1 right there. And then we got to give 5d 1 also. And there are your 58 electrons. What about our noble gas notation? Well, what's the nearest noble gas to Cerium? It's going to be xenon, right? Can't be radon because radon comes after it, so it's going to be xenon. And let's look at our shell here that deals with the rest of it, our valence shell. So the final guys are, it's going to be this right here. Here's our valence shell. It's got our last shell in it, which is the 6s2. So we're going to go 4f1, 5d1, 6s2. What about our quantum numbers? Well, when we look at our quantum numbers, the first thing you want to say, oh, it's in the 6th period, right? Well, look what block it's in. It's in the F block. So it's n minus 2. So it would be 6 minus 2, which means 4. So the n value is going to be 4. The principal quantum number is 4. Since it's in the F block, the principal quantum number is going to be 4. But if it's in the F block, the angular momentum number is going to be 3. The magnetic number, okay, it's going to be the first one, so it's going to be minus 3. And last but not least, what is our spin? Well, our last arrow is certainly pointing up. See that? The last arrow is pointing up, right? So we're going to call that 1/2. So our quantum number should be 4, 3, negative 3, 1/2 positive. Well, that's it, guys. You be snarly, and we'll see you back here at Mucine Chemistry.